Go to. So it looks like I'm changing maybe about -1 and maybe about 2. It doesn't have to be exact. I know this is going to be a parabola. And I know, or I hope you have noticed, my steepest part of the slope, so my maximum or my minimum, is going to occur halfway between here. So maybe around 0, a little past 0 maybe. So I'm going to come here. You think it's going to open up or down? And why? Why? Right. I was getting myself confused for a minute. I was looking. Slope's positive, so it's going to be positive. So I'm going to be coming in this way. I'm going to go down. It can't be 0. I'm going to go down a bit. Something like that. Is that what y'all got? Yeah. As long as you got it where it's crossing. How about the parabola? I know I'm crossing it too. Positive, negative. Just kidding. I was like, what are y'all talking about? It's always a line. Positive, negative. Cubics will derive to parabolas. Parabolas will derive to lines. Lines will derive to horizontal. Like what? The line? Or a parabola? Yeah. Did I do that yesterday? Surely not. Maybe I did said something wrong. I'm sorry. Okay, well the takeaway here, if it's a parabola, it's going to be a straight line. And here we go. Now we get into the slightly harder ones, right? This is actually always increasing on this piece. Do you agree or disagree? So it doesn't look like I'm going to have any place where I cross the x-axis, right? I'm always positive. So what are you thinking? So if you think about these slopes, are they getting bigger or are they getting smaller? Bigger and always positive. So I'm going to do something where, and I'm hugging this specific value, and I'm thinking that value is starting to even out closer to 0 that way, right? Does that make sense? So I'm thinking it's going to hug 0 this way, and it's just going to increase like this. Is that what y'all got? This one, same thing. It looks like it's increasing and it's evening out to a 0 slope as well. So I'm thinking it's going to do like this because it's positive also. Yeah. No, it doesn't have to be. No, it probably is over a bit. It's going to actually need to be over here where this one has an asymptote. I like to draw them right under each other. I think it's easier to see if you draw them right under the side and not right beside. Oh my gracious. Okay. Same thing here. I'm always increasing, so I'm going to stay above the x-axis. Getting bigger and bigger and bigger. It's going to look the same, I think. Is that what y'all got? This piece looking about the same. This one is a negative, getting closer and closer to 0. So I think this one is going to do more like this. And now I just need to worry about this piece in the middle. So this is a parabola in the middle, right? Looks like here's my maximum. So it's going to cross over. I'm going positive, negative, right? But it's not an actual parabola. So I think, because I have these asymptotes in here, I think what's going to happen, it's going to cross at 0. It's going to do something maybe like that. Because even though it looks like a parabola, it's not an actual parabola, so it's not going to derive to a straight linear function. And I know it's not because I have these asymptotes here. If it was a parabola, it wouldn't be hugging an asymptote. It would keep cross over that asymptote at some point, so it's bounded. Does that make sense? Y'all are getting these a lot better than previous classes. I don't know why, but it's not a bad thing. Next one, let's see. Always negative, right? I'm decreasing, decreasing, decreasing. I don't ever cross. Doesn't look like I'm approaching 0. Looks like it's going to be the same again. This one's decreasing, crosses here, so I'm going to start negative and move positive. It looks like it's going to do something like, where am I going to 4? I'm going to curve a bit. Do I? Like flatten out more? Yeah. And if you went through and you actually looked at what these tan lines look like, it'd be a little easier to, there you go. And this one, positive instead of negative, but still coming to 0, so it's going to do something like this. Oh, let's see. Increasing, I'm going to mark here. Somewhere around here, somewhere around here. My zeros, steepest slope at 0. So let's see. About -3, about 3, something like that. Bless you. Positive, negative. 0 is my most negative. Maybe something like that. What y'all got? These are not, they don't have a very steep slope here. So I'm thinking they're going to kind of round. They're not going to shoot straight up like a parabola. Does that make sense? On your quiz and test, yours will be more like a piecewise function like we did in class the first day, where you'll just do the derivative under it. Okay. Y'all okay there? Sketching grass. Yeah, go ahead and turn it in if you haven't. We are simply going to talk about places today where f of x may be not differentiable. Or I should say non-differentiable. Points, functions, or places. And we've actually touched on this several times. We just haven't given them official names yet. We'll talk about official names. So far, we've given 2 criteria for it to be differentiable. What are those 2 criteria? continuous continuity, left-hand limit, that's right. Coming in from the left and the right, those slopes have to match. So if either one of those fail or both fail, they don't have to both fail, then it's not differentiable. So we're going to look at some specific examples of things that fail and why they meet those criteria of failing. But there are 3 specific examples. 4 if you count continuity. Obviously, I'll put that one first. Obviously, discontinuity rules out never differentiable. Okay, so those are all of our different types of discontinuities. Not any one in particular. Your removable. Removable means a what? A hole. Jump. What's another one? Asymptote, which is called an infinite discontinuity. What's another one? There's one more. Oscillating. It's that new one we talked about, oscillating. So anytime we have one of those types of discontinuity, we can already rule out differentiability at those points of discontinuity. I should say that. Points of discontinuity are non-differentiable. So then we talked about where the left-hand derivative is different than the right-hand derivative, which simply means that as I come in, those slopes are not the same. So what I want to talk about is 3 different ways that that happens and some common examples of that. I'll give y'all a minute to catch up. Camden made the news again. We're charging so much for our City of Camden bills. You thought there was, or there is? You thought that's what I was talking about? I don't know. Wouldn't surprise me though. Y'all got that? All right, other places where it fails to exist, and we're going to talk about 3. The first one is what we call a corner. And this is just where my left and my right sides come to a sharp point and very obviously do not match. They're not approaching the same value. Can you think of one very easy parent function that has a corner? Absolute value. That's exactly right. The absolute value of x looks like this. This is what we call a corner, and it is not differentiable. And I think we've talked about this one, differentiable. The derivative from the left, this has got a constant slope. This has got a constant, but they're not the same. They're never going to be the same. They're never going to approach the same value. So that's a corner, not differentiable. Then we have what we call, yep, yeah, tell me when you're done. They're very obviously completely different as you come in. They're not approaching that same value. It literally looks like a sharp point on the graph. That's what you're, graphically, you're looking for that sharp point and you know that it's not differentiable. And that's really what we're doing here is we're examining graphically instead of as opposed to algebraically like we've been doing. The next one is what we call a cusp. And it does come down to a point, but kind of oddly so. This is what it looks like. I have a graph that does this. this point, this is my cusp, not cusp. It's not differentiable. This is pretty much what a cusp is always going to look like. It's going to look like two wings coming in this way. What's happening is my tan lines, they are approaching the same value, but what value are they approaching? Not 0. 0 is this way. What would that be? What kind of slope does a vertical line have? All right, this has a slope of 0. What kind of slope does this have? Which is undefined. If my slope is undefined and they're approaching an undefined value, well, then that means I can't take the derivative there. Does that make sense? See how it's getting up to a straight line? So I can't take, because derivative is the slope of the tan line, if the slope of the tan line is undefined or is approaching an undefined value, I can't take the derivative. So that's a cusp. All right, so opposite left and right hand derivatives, these are not opposite, but it's approaching an undefined value, which means can't do it. Vertical tangent is the next one, and it's about the same thing. It's very similar to a cusp, but remember I told you there's only 3. This is the 3rd. Vertical tangent looks something like it's almost like an inverted cusp. So here's my problem, right? At this point here, I would have a vertical tangent if I came in. Just like the cusp one that's coming into the same thing here, my slope is again approaching an undefined value, right? If I did the tan line at that one point, it would be straight up and down. So again, a vertical tangent would have an undefined slope, which is not differentiable. I should have given you some examples of graphs. Okay. These cusps are something like x to the maybe a rational exponent, 4/5, something of the sort. That's what vertical cusp, or that's what cusps look like. Vertical tangents might be something like the cubed root of x would have a vertical tangent at 0. You'll be graphing these and looking at them though. I think those are actually ones from your homework. Yeah. And we talked about left hand limit and right hand. All right, y'all okay? Types of non-differentiable functions, or points where the function fails to exist or does not exist. Let's look at number 1. Hey, y'all. I do number 1. Let me show you how to do this on the calculator so it'll save some time. Take an easy one. F of x equals x squared. If I want to know what the derivative at 3 of this function is. The only way so far you know to do it is how? The difference quotient, right? Or the alternate formula. But I want to show you, and this is an easy one. It wouldn't take you long to do it with the difference quotient, but I want to show you how to do it on your calculator. Now remember, this is just a check, so you still have to show your work, but so that you know how to do it. Go to Math, and down to number 8 where it says Inderiv. You'll put your function in first. So I just want to do, what's yours say? Oh, okay, I'll show you what to do in just a second. Hold your, here, can I use it too? Okay. All right, let's see. I need to put an x after to show what variable I'm taking the derivative with respect to, and then what value I want. What did I say, 3? And you should get 6. Okay. So if you have this kind of calculator, you put the function, the variable you're taking the derivative with respect to. So that's your dx, dx. The x is here. So this, for this case, whatever this variable is, it's going to be the same thing here. All right. You'll need to put parentheses around your function if it's a complicated function. And then the point, that's your a. Okay, that's what you're taking with respect to. If you have this kind of calculator, it's a little bit easier, a little bit nicer. D dx, because you want it with respect to x, you put your function here, so x squared, and then when x equals 3. Nice little handy feature on the calculator there. Well, you still have to show your work. We will get to some, you'll have a set in your homework that says use the Inderiv function on the calculator, because you'll have some multiple choice questions that are calculators that you'll need to do that. But they'll be so hard you couldn't do them by hand. The easy ones that you can do by hand, they won't let you use the calculator on. All right, so let's see. Let's do number 1 together. Number 1 is compare the right hand and left hand derivatives to show that the function is not differentiable at point P. So I'm not defining it as just being a corner or a cusp or a vertical tangent. Instead, what I want to do is show the derivatives as they come in and that they are not the same. This is the function y equals x squared. This is the function y equals x. Well, you know what? Which one? Grays or calculator or non? Which one's what? Okay, well, this is a calculator problem. But make sure you know how to do this for your quiz and your test and everything else. Make sure you can do the difference question. This is nothing more than a piecewise function, right? If I wrote this out, this would be f of x equals x squared when x is less than 0 and x when x is greater than, one of them's got to be equal to it, doesn't matter which one, to make it continuous. And it tells you that this point is 0, 0. So I need to show that the derivative from the left is the same thing as the derivative from the right. So essentially what I need to do is find the derivative of x squared, so derivative at 0 of x squared, and then the derivative at 0 of x, and show that they equal the same thing or they don't equal the same thing. That's how I'm going to prove that the derivative does not exist. Yeah. Yeah, no, that's fine. So if I wrote this as a piecewise function, this is what it would look like, right? And so what we've been doing is working with these piecewise functions and showing the limit as h goes to 0 from the left, and that's where I would use this function. So f of x plus h minus f of x over h. But in this case, it's going to be x squared. I need to know if that equals the limit as h approaches 0 from the right. This one I'm using x squared. This one I'm using x. Same formula. I'm writing the formula because yesterday I didn't write it and you'll got a little confused. So now this would be, does the limit as h goes to 0 from the left, x plus h squared minus x squared over h. And what's the point that I'm looking to test when x equals what? 0, right? So when x equals 0 means I'm going to put a 0 here, a 0 here, a 0 here, and a 0 here. So the limit as h goes to 0 from the left is h squared over h. Is that the same thing as the limit as h goes to 0 from the right, 0, 0, of h over h? No, because over here, that's going to be 0, and over here, it's going to be, they're not the same, which therefore shows me that the left-hand derivative and the right-hand derivative are different, so it's not differentiable at that point. That doesn't mean it's not differentiable everywhere, it just means at that point it's not differentiable. Does that make sense? Some of them are just going to be quite obvious in what they are. Let me look at a couple. We'll just do these out loud together because a great page. Teachers are having to do quite so much. Hi, you mean differentiable at the points given or not? So directions say, here's the graph of a function over a closed interval. What domain points appear to be differentiable, continuous but not differentiable, and neither continuous nor differentiable? So look at number 7. It's definitely not continuous, right? It's got a jump discontinuity. We agree. Even though this is filled in here, it still hasn't removed the discontinuity altogether, so I can't say that it's removable. So it is a jump. So then it asks, is it differentiable? What do you think? What point is it not differentiable? At 0. It's not differentiable here because of the discontinuity, but everywhere else, it looks okay. Do you agree or disagree? So at what place is it neither continuous or differentiable? 0. Does that make sense? How about number 8? Not continuous, another jump, and a removable. Okay, so 0 and 2 would not be differentiable. Do you see any other points? -1. Why is -1 not differentiable? It's a corner. So for this one, I've got a corner, a jump, and a hole that would all cause me not to be differentiable. So it's differentiable on its domain with the exception of -1, 0, and 2. Does that make sense? Look at number 9. Continuous? Yes, this is continuous on its entire domain. It has no discontinuities. However, it has a cusp at 0, so it's not differentiable at 0. Y'all see, does this make sense? Do I need to write this down for y'all, or y'all okay? I'm just kind of talking through it. Y'all good? At certain points, yes. Yeah. I think the first ones they gave you, 7, 5, and 6, look like they're continuous and differentiable on the entire domain. But then I skipped over to the problem ones to talk about. How about number 10? It's continuous. Is it differentiable on its domain? Where is it not differentiable? Negative 2 and 2. What's happening? Corner. They are different, yes. Continuous, remember the limit approaches the same thing from the left and the right. The derivative, if it's differentiable, that means it has a derivative. That means the slope is the same as you come from the left and the right, as long as that slope is not undefined. In this case, as you come in, these slopes of the tan lines are getting closer and closer to undefined. So that's why it's a corner or cusp. Right. So anytime you see literally a sharp point is a corner. So if you ever see a sharp point, you automatically know, no, not going to work. Do you? I don't know. All right, I think that I am going to have you do. All right, we did one together. I'm going to have you do. We'll do 3 and 4. These are by hand. These are the left-hand derivatives and right-hand derivatives. We did 5 through 10 together. 11 through 16, graph and look. Okay, those are graph the function, tell if it's differentiable or not. So you're just going to look, does it have a by hand? That's the difference quotient for those two. 11 through 16 is going to give you an equation. You're going to look at it. Does it have a corner, a cusp, a vertical tangent, or discontinuity? Okay, so those aren't hard. They shouldn't cause you any trouble. Do I need to give y'all a couple to make sure you can use your calculator for the end deriv part? No. But those are graphs. Yeah, I'm going to give you just 3 of them. End deriv. No. Just right, corner, cusp, vertical tangent. Just look at it. Yeah. I think that's it. I think that's good. It shouldn't take you long.